Everyone, and welcome back to the course. Um, we are going to be discussing on mathematical analysis of the efficiency of non-recursive algorithms. And to do all that, we have to first know that this is all about algorithms, right? And we're trying to analyze algorithms, which ones are good and which ones are not good. And as a result of that, we need some form of a plan. We need to know what exactly it is we are dealing with the algorithm, and we need to also be able to establish the order of growth because it's what tells us how complex the algorithm actually is in terms of time and space. So let's get into it. We have the general plan, and what does the general plan entail? It has to first of all give us a clue of what the input size is. And when we're talking about input size, we established about traversal and non-traversal algorithms where the input size might not necessarily be the entire input, like let's say 5 million emails. It might not be exactly 5 million emails. It might be the search key that we have given. And maybe we are asking for emails of people with the name Bamitale inside. We know that the name it will be around the B side of the if it's in an alphabetical order, which is why we need sorting actually. But for an alphabetical order, we know that B is pretty high up, and it's not the entire 5 million or so emails that will be checked. It's around that B section that will now be gone through, and it will be not the full input that actually now constitutes the input size. So we need the parameter to establish that, and we'll look at the algorithm, and we should be able to tell from the actual algorithm. So if it's a sorting algorithm now, since it has to traverse through the entire um, index of an array, for instance, now we can see that the input size is the entire element. While we are dealing with searching, we know that for binary search, it's even smaller because it's going to be dividing for each iteration. That is the decrease by constant factor method of designing algorithms, which is under brute force. Now we know that we want to establish the input size. Is it n or is it not n? And we just need to know. That's the first thing we need to do. Then the next thing is to identify the basic operation. What is the basic operation? The basic operation is one that contributes the most to the runtime. And then if you have a lot of for loops, the innermost loop will probably be the one. If there's only one loop, then that thing that is happening inside that loop, depending on whether it is a comparison or it's replacing, whatever it is that is there, usually used to end up being the stuff. And please let common sense guide you. You don't pick else as the basic operation because it's that is just maybe it's the control structure. It's not exactly saying anything. Comparison, replacement, division, multiplication, all of those can function as a basic operation. Now, the next thing we need to do is to check if the basic operation repeats only because of the input size. That means in the case where we don't really care about the parameter, the size being maybe dependent on the search key or some other values, like maybe the position of the search key on the list, or checking for things and then having to know where they are on the list. If we don't have to deal with all of that, then we can just go on without worst case, average case, or best case, which I can just do. I can just do the thing. I can just do the thing. I can just go straight into the count. But in the case where there's something like there's a best case and there's a worst case, like for instance, let's say you are searching for Zacchaeus Zebedee through a long list of things. You know, Zacchaeus Zebedee is probably one of the worst cases in in a list. Because both of them are ZZs, and for names with first name and surname, that's like that's the worst case scenario. So Zacchaeus Zebedee is going to be at the bottom of the list, and because of that, it's going to constitute an input size that is basically almost the entire element because they have to search from A to Z, and then it's at Z that they'll find him. You get the picture. So if in the case where it's not only the input size that determines how many times the basic operation is repeated, then we have to investigate either the worst case or the average case. But the best cases aren't so valuable because I mean it's not exactly showing how the operation even truly works because it doesn't really do much of anything. Now, moving on to the next thing, what happens? We now need to establish the sum expressing how many times the basic operation was run. Okay, how many times was the comparison operator done? Once, twice, three times, four times, five times. On what basis? Is it n minus one times or n times? Depending on the algorithm, it has different effects, and then as a result of that, we have to express sums. And then there are some rules that we'll look into, some manipulation and actually some formulas. And then finally, we use sum manipulation, which is after we get the sum to now get the order of growth. Order of growth is the one that tells us how complex our algorithm is, and that's what we really want to do with. So Having said all that, let's talk about the possible sum formulas. Say you have a sum of constant additions. I should stop doing that. Say you have a form of a sum of constant additions, like let's say 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times, or in this case u times. This is it over here. So this spans from u like for this long. That's how long it spans. So from the start to the start here plus to this plus 1. So the formula for constant additions, like let's say 6 plus 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 6. No, in this case, it's just better to just go 1, because usually we don't have 6 comparisons happening and everything. And this is a formula we don't want to adjust too much. 1 is not I, and as such, we have to be careful what value is actually there because it's a constant. So let's say we have 1 plus 1 plus 1 plus 1. This is going to be very, very important, very, very important down the line. So I want you to remember this formula, that if we are having 1, like 1 is adding for u amount of times, while I is starting from 1, then the formula is the upper bound, which is u, and the lower minus the lower bound plus 1. That's the formula. The upper bound, u is the highest number, and then I is the smallest number. That is the biggest subtracted by the smallest plus 1. This is the formula for this sum. Now this is one of the more common sums we can have when we're having summation of I, and I starts from 1 all the way to n. So we're having 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, blah blah blah. The formula for it is n into bracket n plus 1 divided by 2. To do you well to remember that, because it's one of the valuable stuffs. We need it. These ones are very, very crucial. You do not want to forget these first two, particularly u minus I plus 1. That's for sum of ones. For sum of I, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way to n, we have to do n into bracket n plus 1 divided by 2. And if we open this bracket, we open the bracket, we have n squared plus n, right? And then if we are multiplying that, we have half n squared plus half n. But half n can be disposed because we are dealing with the highest degree of the polynomial. So we can just approximate all of these to half n squared. Now this one is for I square. This doesn't happen too frequently, but at least just have an idea that when you have I square, look at this. This is for I. This is I alone. I alone is given half n square. I square is given half n cube as the approximate. You might want to ignore this. This won't help you very much. But this half n 1 over 3 n cube. Now when you have ik, I raised to the power k, that will just be 1 over k plus 1 n k plus 1. You get, because for I raised to the power 1, it is 1 over 2 n square. For I raised to the power 2 is 1 over 3 n cube. For I raised to the power k to be 1 over k plus 1 n k plus 1. Remember these three guys, they are very important. However, looking through these other guys, you can try and look at them in your own time. Where we have a raised to the power I, 1 plus a square plus that, we have a raised to the power n plus 1 minus 1 over a minus 1. And then when you have I times 2 raised to the power I, where we have 1 times 2 raised to the power 1, 2 times 2 raised to the power 2, 3 times 2 raised to the power 3, all the way to n times 2 raised to the power n. We have n minus 1, 2 raised to the power n plus 1, plus 2. You can want to know 1 over I as well. 1 over I, when you had 1 plus 1 over 2 plus 1 over 3 plus dot 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 all the way to 1 over n, will give us ln n. Then an Euler constant, I forgot, I think 0.5883 or something like that. So that's what this guy is going to give. And log I, when we are doing the summation of all the logs, we have n log n as a result. But I want you guys to know these guys by heart. These ones are very, very important, because we'll be using them in the coming some expressions and manipulations. So looking at now the sum manipulations, let's say we have a sum ready. We've done all our stuff. We now have a sum ready and we want to work on the sum. So how does this look like? Take a look at the first one on the list. Okay. Take a look at the first on the list. We can see that it is sum I is equal to 1 all the way to u, and it is c AI. Now if you notice, you would see that this C is not being directly affected the by the summation. It's constant, it's just there, right? And since it's constant and then there's a here, if you know what we do with when you have something like 1x plus 2x plus 3x plus 5x, what do? We take x out and we have 1 plus 2 plus 3 plus 4 plus 5, oh no, plus 5 rather, plus 5. Since we can factor out x out in this normal summation, we can do the same thing in the other one we just did now. So that is for that. The next sum manipulation is if we have the summation from I equal to 1 to u, and then we have ai plus or minus bi. We can separate the summations where we have the summation of ai plus or minus the summation of bi. So we are just able to separate them, but this is still the same as this. We will use that. It's very, very important. We need that in the future. So this particular summation from I is equal to 1 to u on a minus 1, we can actually separate the same summation to have different upper bounds and lower bounds. Take a look at this. It goes from I is equal to 1 to m, now a new value m, and then the ai remains constant, it doesn't change, plus then we created a new starting point. So the starting point of this guy is the plus 1 of the ending point of this guy. So we just created two sums of, like, just separating them. It's like partitioning 1 plus 2 plus 3 plus 4 plus 5 plus 6 into 2, where we cut it here. So 1 plus 2 plus 3. So this is summation I is equal to 1 to 3 on I, and then plus, then we take this guy, summation for I is equal to 4, that is 3 plus 1, all the way to 6 on I. That's what we just did there, and it's actually very, very legitimate and it's normal. You should expect something like that to show up, and just leave it. Then finally we have this guy where we are having a subtraction going on, and then I, so we are subtracting the biggest value by the current value from the past value, right? So subtracting the current value from the past value. If we keep on doing all the subtractions and then add all of this, the results of that, we'll have a of the biggest value, the upper bound u, minus the smallest value, minus 1. So that is that about that. Moving on. Now we have an example, and we use examples to show how that general plan is. And if you remember the general plan, number 1, determine the input size by checking the parameters. Number 2, identify the basic operation. Number 3, check if the number of times the basic operation is executed is dependent on the number of the input size or some extra set of conditions. Then number 4, set up some sum expressing the amount of times that the basic operation was repeated. And then number 5, do some manipulation on that to get the order of growth. So that's the general plan. That's what we're trying to do. So now, how do we put that into actual algorithms? So let's look at this guy. We have the maximum element. This is the problem. We are trying to design an algorithm for outputting the value of the largest element in an array. So what does it take as an input? We have already talked about what it determines. The maximum element, it takes the array from 0 to n minus 1, and then the output of that is the value of the largest element, not the index of the largest element, the value of the largest element. So the max value will be the actual element itself. So if we look at it there, we see that the max value starts initially with the a at index 0. So we are saying the element a index 0, that's the beginning. That's actually the start of the array. So the first thing is what we take as the maximum value first. Then we run it into a for loop from I is equal to 1 to n minus 1. So from the next value after the second value, we're starting from the second value now to the last value. We want to check if ai, which is the current element on I, which is the next one, or if the next value, I is equal to 1 right now for the first iteration, I is equal to 1, which means the second stuff, because the first one is 0, then the second one is 1. So if I is equal to a into the index of I is greater than the max value, which was a at index 0, then we can just replace the max value with that current um, um, index and the element rather. So now we're having max value is equal to ai, where I is the index. So it will keep doing that. So if a index 3 is greater than a index 1, then we replace that a index 1 3 max value will be replaced with a index 3. And then if a index 75 is greater than the previous one, then we replace the max value with a index 75, and then after all of that is done, we return the max value. So now let's do some analysis on it. Question 1: what is the input size of this particular algorithm? Looking through this, we see that it goes from from I1 to n minus 1. However, is there a thing about worst case or best case in this place? Let's take a look at it closely. It's going to search through everything, right? It's going to check for every single element of the array. It will compare, it will check, and then after it sees that okay, we've gotten to the end of the array and we have already computed for the biggest size, just return max value n minus max value. So we don't have to worry about dealing with things like okay, best case, worst case, since everything is going to be taken in. So having said that, the input size is actually the total number of elements n. Since we are going from 0 to n minus 1, that is index. So the total element is actually n. So the input size is n. It's not dependent on any other value than that. So what is the basic operation? The basic operation is also this guy over here. And then let me just write that in the plan. Okay, so we have the plan. We've done. Let me see if I can do something that it just messes up. So we have the plan. Number one, what is the input size? The input size is equal to n. Why? Because it's going to traverse. It's a traversal algorithm. It's going to check everything for which one is the maximum and then to use that. Number two, what was the basic operation? Let's look at that real quick. So the basic operation here, in the innermost loop, we have this guy and we have the replacement going on. But this particular one will contribute the most to the runtime. It is the one that does the most work. It's not every element of AI that would be greater than the max value. So this one it won't exactly happen every time. But this one is going to happen every single time because it's going to have to check. And so the key comparison is one of these is in this case the basic operation. The key comparison itself is the basic operation. So having said that, basic operation is if a ai is greater than max val. So that's the basic operation. So then what next? We need to check if we need to investigate the worst case, best case, and average case. But since we are going to traverse through everything anyway, we don't have a best case, we don't have a worst case, we don't have an average case. We just have the count of the operation because it's going to do everything anyway. So there is no need to investigate best, AVG, or worst case. Then number 4, now we have to deal with making the sum formation of this. So let's go back and check our guy. We will be using the for loop as the basis of the formation, but then let's check this particular expression since it's the basic operation we are dealing with. For each iteration how many times is the basic operation performed? Once, because it's going to have to work with the current I to check if the max value is equal to the element that is in that index. So since it only happens once, for I is equal to 1, for I is equal to 2, it will do only one comparison. I is equal to 3, it will only compare once again. So for all the times where the for loop is running, the value is actually just is just one. It's just one time that the operation is being repeated. So it's not like we are comparing n minus 1 items, then n minus 2 items, or n minus 3 items, or n minus 4 items. We are just doing one comparison each. When we start dealing with things like sorting algorithms, then we can now start talking about the different things that can be happening, like n minus 1 combination, then n minus 2 combinations, then n minus 3, all the way to one comparison, rather, not combination, until we don't compare anymore. So back to this, we know that the summation is just going to be from the start to the end is where we will put as the upper bound and the lower bound in this place. So the lower bound is 1 all the way to n minus 1. And then what is the operation that is being what is happening? It is just the addition of one comparison, one comparison, one comparison, each time one comparison. So going back to this guy, the sum form will look like this. Since we have I is equal to 1 all the way to n minus 1, we will now have 1 here, because for each iteration is just one comparison, one comparison, one comparison, one comparison. So what would this be equal to? Remember that formula that we had here. Look at this. Look at this. Look at this. So when we have a lower bound and an upper bound, and then it's constant 1, where we're having 1 plus 1 plus 1 plus 1 all the way to the end of this guy, you can say that the top minus the least plus 1. So back into this, what is the top? The top is n minus 1. What is the least? I is equal to 1. Then, so this is this minus this plus 1. So 1 minus 1 plus 1 is just going to be nothing. So we have n minus 1 is the result of this. So we know that this is the sum. This is sum, and we don't need to do some manipulations to this, because I mean it's very simple. This is about all we need to do. But then now, how do we equate this to the order of growth? We can just say that n minus I minus 1 is an element of the big O of n, or rather, if you say big O of n, it's actually not wrong, but then it's better to just say big theta of n, because big theta is dealing with same rate, growing at the same rate. So if we use big theta, we say that this guy is has the same growth rate as this guy, and since they are both of the same degree of, they are both linear, the degree 1 of the polynomial, we can actually just say this is very true. And then since we have the order of growth, we have perfected and we have finished and completed this algorithms analysis. So moving on to the next example. So the next example is a uniqueness problem, and I want us to also be able to identify algorithms in questions. Like we could be told that, okay, what is wrong with this algorithm? We could be told, okay, create an algorithm for a uniqueness problem. So you have to also note that you might have to you might have to write out the algorithm. But then let's get into it. We don't have much time. So look at this. We have this unique element. What does it do? It determines whether every element is unique in an array or not. And if we look at it, the input is an array from a to n minus 1, the index, and then to return true if all of the elements are unique and false if it's not. And then it will run from, okay, for I is equal to 0 to n minus 2. I will explain why this is. And then j is equal to I plus 1 to n minus 1. Do this. So picture this like this. We have an array, and let's say we have 1, 3, 5, 7, 9, 11. And then this is 0, 1, 2, 3, 4, 5. So this is, let's say this represents n minus 1, right? And this represents our 0. Now picture it with me. If I is equal to 0, we are talking about this guy. And at this same iteration, j is also now going to iterate under it as j is equal to I plus 1, right? So j will be this guy. So if I is this guy, j will be this guy. And if j is this guy, we are now comparing in this place that is this guy equal to this guy? If the answer is true, then if it is, then we return false, that this entire algorithm doesn't have every element being unique. Then how about this n minus 2 and n minus 1? I started from a, right? and then j is starting from here. The last value of I would be this guy over here, n minus 2, while this will be the last value of j, n minus 1. So for the final checking, this guy will check this guy if they are both equal. You get, so it will be going from this guy to do for this guy, then to do for this guy. So it will do like this, do like this, then do like this, do like this, then do like this. You see. Now we have to also ask ourselves the questions that number one, is the input size dependent on just the entire number of elements in the array? Not exactly. No. And why is that? If at the beginning we have 1 and 1 as the elements, not like the elements 1, 1, 3, 5, 7, and then ai is on 1 and aj is on 1. By the time this will do, it will return false instantly. So there's a best case scenario. What about the worst case scenario? If we have 3, 5, 7, 9, 9, you check for these guys, check for these guys, check for these guys, then finally now check on the last point and then realize that it actually is not a unique. And then when it finds it out, this is like the worst case scenario. Another instance is it's check for 3, 5, 7, 9, 11. It check for everything and then eventually find out that it is actually unique. So we have a worst case scenario here. Since we have a best case and we have a worst case scenario, we don't really care too much about the best case, so we'll focus on the worst case, right? So now let's look at the plan. What do we say about this stuff? Determine the input size of the algorithm. And the input size is n, and also input size is just n, but it depends on the position of the accurate. Let's say we have an accurate this thing here on the position of unique non-unique elements. So the input size is n, we have a large stuff, but then it also depends on the position of the non-unique elements. We are just acknowledging that despite the fact that we are considering an entire array with of elements n, it depends also on the input, on the position of non-unique elements. So let's say we find it early, then the input size is no longer this guy, it's now the position at which that thing is found. Moving on to the next, we have to deal with the question, what is the basic operation? And if we look through this page, the innermost loop is a comparison here. So this is the basic operation. Basic operation if ai equal to aj. So the third is there a best case, is there a worst case? Yes, there's best case, there's worst case. So what do? We want to investigate the worst case. And what makes up the worst case? Number one, the array has unique elements, no two equal elements. That's number one. Number two, the non-unique elements are in the last indexes. So this is the worst. So we are computing the C of worst case here, and that's the count of the worst case. So let me scale this down to create more room. So what are we basically doing when we look through this guy? If you check it, you see that the comparison is also just one comparison, but there are two for loops. So there will be two summations, not one. And then we have to consider this first formation. It goes from 0, the lower bound, to n minus 2, and then the second formation goes from I plus 1 to n minus 1. So but it's only one comparison that's occurring there. One comparison, one comparison, one comparison. Is AI equal to AJ? If not, is the next AI equal to the next AJ? If not, is the next AI equal to the next AJ? So it's one comparison that's occurring each. So what do we now have? We'll compute the first summation, which is from I is equal to 0 to n minus 2. I is equal to 0 to n minus 2, and then we have, we're just doing one of that, and then we have dot, what's the next guy? J is equal to I plus 1, and let me just remove this dot, and then we have n minus, yes, it's n minus 1. So back into that, we just have n minus 1, then I. Having done that, we now have to deal with this summation first before we deal with the summation. Then we need to bring in the summation manipulation, right? Since we're doing summation manipulation, we will have to do what we did for the previous one, where we check for the upper bound, and no, yeah, we don't have any operation going on inside this place. I should mention that. I'm very, very sorry. We don't have an operation going on inside that place. They are not exactly two different things that is going on. This is what we have. Two for loops, but then the actual basic operation was happening in the innermost loop. So forgive me for that error. So we have that, and we've said that we are going to have to do u minus the lower bound plus 1. And then for this guy, what is the u minus lower bound plus 1? We have n, we have the summation of the previous one, n minus 2, I is equal to 0. Then the lower bound, the upper bound is n minus 1, minus the lower bound is I plus 1, then plus 1. So if we do the subtraction, we know that we are going to have the minus, this guy will become minus, and then minus plus 1, minus 1 plus 1 is going to remove that, so we'll be left with summation n power n minus 2 rather, and I is equal to 0, and all of this will give us n minus 1 minus I, right? Since that's going to give us that, we are in another summation. Let me just bring that down all the way here. We have summation n minus 2, I is equal to 0, then n minus 1 minus I. Now there are two ways this can go, but I prefer the second way. What does the second way look like? If you notice, I is equal to 0, right? So if we start imputing the value, we have n minus 1 first, then we have n minus, I will increase to 1, right? N minus 1 minus 1, that is n minus 2, then the next n minus 3, n minus 4. So we can notice that it's going in a decreasing order, right? All the way till we reach n minus n into bracket n minus 2, right? So when we reach that point, we know that the n's will disappear and then we'll be left with 2. Then if the next thing that will come after that will be 1, so this goes all the way down to 1. So if we put that summation, we're just basically saying we're having n minus 1 n plus n minus 2 plus n minus 3 all the way to 1. Since this is the reverse, the formula for this particular sum form is n into bracket n minus 1 divided by 2. Note that the previous one we're dealing with for increasing order, when we're dealing with I, right, is okay. Yeah, I should mention that this is equal to summation I is equal to 0, n minus 2 I. That's what's happening here. But then it's not exactly I, but it's like the inverse. It's related to this guy somehow. So having that, the formula, you can check online, you can verify what I'm saying. The formula is n minus 1 divided by 2. If we were to look at this, we will know that this is a this would, when we expand this guy, we have n square, and since we know it's n square, we can just say that this is an element of the big theta of n square. This is the order of growth for this particular problem. I think for the sake of time, it's better for us to just have this one at the back of our minds instead. The second one goes so far, we have to split, then do multiple operations and divisions and everything. But this one is simpler for you to remember, and it will be good for you to have this. Note that n minus 1, this guy is saying this guy in short, and then this is the formula for dealing with it, and that is part of the n squares big of O. All right, I should do one more. So the last question is the matrix multiplication question. So for the matrix multiplication question, we have to know that the we are taking in two matrices, right? And we are multiplying, the input, it multiplies two n by n matrices, and the input is two n by n matrices. The output is a new matrix. C is equal to the multiplication of first matrix A and the second matrix B. So we have a for loop going from I naught to n minus 1, another for loop going from j naught to n minus 1. So this helps to initialize the C, because it's I and j that we are using for the value of the n by n for C. So when we get to this k, this is the part where we actually pull out the calculations, and it is the innermost loop. And what does this give us is we are just saying C of I and j is going to be increased by the multiplication of these two values. It's actually that same thing of matrices of this guy dividing this guy, multiplying this guy, rather this guy, 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 then this guy, this guy, this guy, this guy, this guy, this guy, and so on and so forth, like that. So that's what we are basically applying with this. So take note of that. What the first questions in the general plan is, number one, what is the input size? We know that the input size is going to be depending on, since we are doing all of the matrix, we are calculating everything, right? We are multiplying every element. So we are multiplying every element. We know that the input size is dependent on the matrix element n. So the input size depends on matrix element n. Now the second question is, what is the basic operation? If we check through, we see that there are two things. There's the addition and then there's the multiplication. But remember when I was talking about the basic operation, that the one that takes the most running time is the multiplication. So the basic operation is the multiplication part of the innermost loop. So we are just going to write that out. So A I K star B J B K J. So that's the basic operation. The third question is, do we have to do worst case, best case for anything? It's traversing everything in A and everything in B, so we don't have a special case, we don't have a bad case, we are doing everything all together. So we only have to do the count of the basic operation. So we just have to do the count of n. So doing that, the next question is, now what is the sum form of that? Since we are multiplying individual values, right, of multiplying individual values of this guy, we are doing, okay, for the instance of I and k and j, we are doing one multiplication for every instance. What are we going to be having? We are going to be having three sum forms, three summations rather, since it's three for loops, and then we have one in between here because it's only doing one thing after these three for loops have been looped. So for the first for loop, it is from I is equal to 0 to n minus 1. The second one is from I is equal to 0, j equals to 0 to n minus 1. The third one is k is equal to 0 to n minus 1. So they are exactly the same. So I is equal to 0, n minus 1, j is equal to 0, n minus 1, k is equal to 0, n minus 1. And then, so remember what we did with the last one. We say u minus k plus 1. So u is n minus 1. What is k? What is k? 0. What is then plus 1? So we have n. So the next, what we will just have eventually is summation n minus 1 I is equal to 0, summation n minus 1 j is equal to 0, and then we put n because we have done for this first value. Then if you recall that in the some manipulation, let me see if I can find it. Remember this guy where the constant that is not being affected by this by the increment of the summation can be taken out of this. We will do the exact same thing with this guy. So since n is not really doing anything anymore, we can bring n out of everything. So n minus 1 I is equal to 0. Then we have n minus 1 again, j is equal to 0. And what will be left after we factorize out n is going to be 1 that we'll be left with. And since we are going to be left with 1, we'll do the exact same thing for n minus 1 and j is equal to 0. It will give the same value n here. So what we have n minus 1, I is equal to 0, n again. And then we'll do the thing we did previously about factoring out n. So we'll have n square summation n is equal to n minus 1, I is equal to 0, and then 1 will be here. So finally, when we do the exact same thing we did here, where u minus I plus 1, we'll have n square times n, which is n cube. And we know that n cube is going to be an element of the big theta growing at the same rate, the order of growth growing at the same rate as n cube. So this is, we've done for all the plans, we have done for the plans and everything, and we have our answer. So thank you for watching. I'll see you in the next video.